great pleasure to introduce Mert Gurbuzbalaban from Rutgers University, who's going to give our next talk.
Right. Thank you very much for the introduction. And I wasn't feeling very well in the last few weeks, so thanks to the organizers for letting me speak in an online fashion. So today I'll be talking about heavy tails in the context of stochastic gradient descent methods. Essentially, I think Murat did a great job of setting up the notation and talking about Langevin methods. We will be in the optimization setting and mostly sticking to sort of optimization algorithms, and we will be mostly talking about stochastic gradient descent methods, which are really key methods in machine learning. I'll be looking into different settings such as centralized and decentralized data settings when the data can be centralized or data can be decentralized. So I will look into several settings, but I will be sticking to mostly optimization in this talk. All right, I think most of you, guys are familiar with stochastic gradient descent methods. But there may be different settings, online, offline, etc. So I'll be just doing a quick recap about stochastic gradient descent methods. And everybody can hear me all right, right?
Yep.
Okay, perfect. So the standard setting in statistical learning is essentially you have let's say we are doing supervised learning. We have the labeled data, input, output, data pairs. And it's random, following an unknown distribution, let's say D. And we have a predictive model. Let's say X is your parameter. Obviously, if you want to train a model when you are fitting the data, you will be doing some sort of loss function minimization. So you are minimizing a cost function to fit to the data. But because the data is random, naturally, you are going for the expectation to get some sort of average fit. So this is a stochastic optimization problem known as risk minimization, and arises in many contexts. For example, in the very, very simple setting, if you are just after fitting a linear model, you could just choose your objective function f to be a quadratic function, and now you are doing linear regression. Essentially, you are doing least squares. But obviously, in real life, a lot of times we need much more complicated models. And for example, deep learning has been a very powerful modeling framework where it made a big difference in different fields, including computer vision, self-driving cars, etc. So in the deep learning context, essentially, you have the input, you have the output. You are still trying to fit the data, but the map from the input and output is highly complicated and non-linear. Essentially, you process the information in a compositional manner, where you filter and average the information and threshold it over the layers in a compositional manner. This compositional structure makes the objective function to be complex. But again, if you choose your objective function f accordingly, you will be covering the deep learning setting. Okay, so this is the general setting. And if you notice here, for the capital function f, I cannot really compute its gradients directly because I don't know the underlying distribution. So what we do is we assume access to, let's say, IID data points. We could sample from this distribution. That's the assumption. So then the idea is to replace the expectation with a finite average. So this is a sample-based approximation to the gradient. So eta here is the step size. And what you are doing here is essentially, let me annotate it for you so that you can see it better. So here, eta is the step size. And based on, let's say, B data points, where B is called the bed size, you are forming a stochastic estimation to the gradient. So these methods are therefore called stochastic gradient methods. So this is the online setting where I am using fresh samples at every step, but there are also offline versions where you would just stick to the to a finitely many data points and I keep sampling the same points. So there are different versions. This is known as the online stochastic gradient descent. So obviously, SGDs, aka stochastic gradient descent, have has been very successful in practice, and people are trying to find out why it leads to good solutions. And obviously, the noise structure plays a key role here, because essentially the noise is telling you roughly where you are going to. So, and then if you consider the noise structure, because you are having the data sampled in an IID fashion, your gradient noise, which is defined as the stochastic gradient minus the actual gradient, will be in the form of an average of IID random variables, right? Because if the data sampling is uniform, when you just take an average over the data, your gradient error will look like an average of random variables, right? So when we hear this, obviously the simplest, simplest theory that you can think of is, okay, let's use something like central limit theorem. If your stochastic gradients has a finite variance, I could apply the central limit theorem, and there are many nice results in stochastic optimization about what happens to the iterates behaving in a Gaussian fashion if you were to average them. But a few years ago, in a joint work with Umut Şimşekli and Levent Sagun, we were just testing this hypothesis. Is it really the case that gradients are behaving in a Gaussian fashion in deep learning practice? And we were quite surprised about our findings. For example, here in orange, what we are looking at is the histogram of the norm of the gradient error. If the noise would follow a Gaussian-like distribution. So because of the norm, you will see a half normal sort of distribution. The orange plot, would be roughly how your histogram looks like if things would be really Gaussian, right? But the blue plots show you what is really going on in practice. The leftmost blue plot is telling you how your gradient noise looks like in the beginning of the iterations. And then the plot in the middle is showing you what happens after many iterations when you are close to being done. What you see is that, in the beginning, you have more like a Gaussian-like structure, but over time, things get more heavy-tailed, at least on this picture for this example. So this was quite interesting to us because in the literature, there was no documentation of heavy tails so far back in 2019. But we thought, even if it's the case, let's say that everything is heavy-tailed, we can still have limit theorems, right? Because essentially there's a generalization of CLT where it tells you that if you were to average heavy-tailed random variables with an infinite variance, then the limit would be an alpha stable random variable where alpha can vary between 0 and 2. Basically, alpha equal to 2 covers the Gaussian case. That's the Gaussian universality class. But if you were to have something more heavy-tailed, then alpha will be less than 2. And in particular, this alpha would tell you how fast your tails decay. So you can think it like you will have only the alpha moment. Anything below the alpha moment will be finite for you, right? So it's telling you how alpha is called the tail index, and it tells you like how heavy-tailed you are, if you wish. All right, so. And in particular, when we tested this in the paper, actually, it was mostly an experimental paper. We tested a lot of networks and a lot of different small ones, big ones, different layers, different loss functions, etc. And we have seen consistently sort of a departure from Gaussianity in the papers, in our paper. And then another finding we had was that mostly the heavier tailed you are, we were seeing better generalization, meaning better performance on unseen data. So intuitively, if you have heavier tails in the gradients, your algorithm will be sort of jumping from Bayesians to Bayesians in a faster fashion. So we could probably show this. And then at least in continuous time. So then, this would make sense in the sense that if you can explore the space better, it makes sense that you can maybe have better generalization. And then, so this work, we were lucky that it got some sort of like an honorable mention award at ICML. but it was very experimental. So we just thought that there are some heavy tails, but we didn't know why they are actually arising. And I think after our work, there were also many papers that proved these heavy tails, very interesting papers. I listed some of them here that also showed them in different contexts. Also, Martin and Mahoney had a really interesting idea. About the same time, they were thinking of heavy tails in the context of weights. So we were thinking more in terms of gradients, and they were thinking more in terms of the sort of the neural network words themselves. So if you wish, those are, they are thinking more in the iterates, whereas we are thinking more in the gradients. But actually, if your gradients heavy-tailed, you will pick it up in the iterates, right? The same thing. If you have heavy tails in the iterates, you will pick it up in the gradients as long as you have some sort of growth condition, right? So this all made sense to us, but a lot of very fundamental questions were open. For example, is heavy tails something specific? Somehow SGD seems to invoke heavy tails over time. You start Gaussian-like, and then you eventually get more and more heavy-tailed. The question is it something specific to deep learning, or is it something that would arise, let's say, in a simple setting like linear regression, right? Another thing is that, for example, if your data is heavy-tailed, it is natural to see some sort of heavy-tailedness in your iterations. But even if the data wasn't heavy-tailed, we were still observing this. So somehow something in the SGD dynamics was causing it. All right. So we sort of, even if you have the light-tailed data in your data, some of the dynamics is nonlinear and such that you get this kind of heavy tails. It would be linear, of course, in the linear regression setting. Okay. So essentially the picture was as follows. So there is some sort of link between generalization and heavy tails experimentally based on our, and others experiments. Obviously, generalization was studied in terms of things like bed size and step size. For example, a lot of times there are interesting work about, for example, smaller bed sizes are typically associated with better generalization in many contexts. There's definitely an association between the problem geometry or the geometry of the landscape in terms of generalization. For example, let's say you find a solution. If that's lying on a flat landscape, meaning that the Hessian has a lot of zero eigenvalues, then in many contexts, it can generalize better, right? And then, of course, there's no definitive answer for this. It may depend a little bit on the application, but the point is that there's a relationship between the Hessian, like how sharp your minima is, versus the generalization, right? And then what we were after is that if that's the case, the red question marks are open. So what's the relationship between the step size, bed size, and the problem geometry versus the heavy tails? And also the question is, for example, how fast you could achieve this, if there is some sort of heavy tail dynamics, how fast do you achieve it, and why do these heavy tails arise gradually over time, right? So these were questions. So what we did was in our paper. So let me tell you a little bit about our work from a few years ago, and then I will tell you more recent results that we have. So first, we started with looking into, okay, what happens in linear regression? Maybe it's a simpler model. If we can understand it, maybe we can have some insights for the more general models like deep learning models. All right, so essentially in the linear regression setting, you have input A, output Y, and X is some linear model. You are just doing least squares type of loss function. And obviously gradient of something quadratic will be affine. But because you are doing some randomization, you end up getting a stochastic affine recursion. Not an affine recursion, but a stochastic version of it, where the iterates xk, right? At every step, they are multiplied with a random matrix. And then there's also an affine part, the additive part. So this is some sort of, if you wish, like a recursion, but a stochastic one. And in the literature, people study things like iterated function systems. And we realized that in queuing theory, actually, there were really nice results that sort of study this kind of recursions. All right. And what we are after is that, let's say, you run your SGD. After a certain amount of time, hopefully there'll be some sort of mixing and there'll be some sort of stationarity. And the question is that at stationarity, what will happen to the tails of your stationary distribution? In other words, we are trying to quantify the decay rate tail index of the tail. So for example, if your index is alpha equal to 3, you are decaying polynomially, let's say the probability that something's larger than t will scale like 1 over t cubed, right? So if your tail index is smaller, like in the red one, you will be decaying a bit slower. So alpha just tells you how fast your tails are decaying in the sense of a power law decay. So for simplicity, let's take something like a Gaussian distribution for the data AIs. But in the paper, we can generalize this as long as you have some sort of growth assumptions on the data, like in terms of like the tails, you could generalize this to other distributions, right? So we are trying to understand alpha, the tail index, as a function of the parameters like bed size, step size, and the Hessian. Obviously, the Hessian here will be at every step you will be having a Hessian estimate because of the sampling. But let's say h is a random variable that is sort of giving you this your h will be your random variable. You can think it as a Hessian estimate. And here's a formula. So under some sort of mild assumptions, what happens is that, remember this alpha, the tail index, actually it has a really nice explicit formula. So it is the solution of this nonlinear equation. I is the identity, eta is the step size, b is the bed size, h is the random Hessian estimate at every step, and alpha is like your tail index. So it turns out that your limit distribution, no matter what step size you use, has a power law decay, and alpha is a solution to this equation. And the way we got this was basically, there were really nice results in the literature about stochastic matrix recursions, and but they were not quite sort of fitting directly to the SGD framework. So we kind of adapted them to our setting. We could push this a little bit also to nonlinear setting. For example, for things like smoothed lasso, you have essentially a quadratic penalty plus some sort of L1 type regularization. So we could still push this a little bit beyond the linear model regime, but we couldn't really go for the general setup. There are also some results about more general sort of recursions in the literature, but it's becoming hard to characterize how the tails behave as a function of things like bed size. When your models get more complicated, we can't really characterize these tail indexes as nicely. So that's a bit of benefit of working with the linear regression setting. And in this model, because everything is so sterile, we have explicit solution and so on. So we can study things like how does the tail index depend on the bed size, and for example, how does the tail index depend on the step size? In particular, what we find is that if you have smaller bed sizes, you will have heavier tails. I mean, intuitively, that makes sense because smaller bed size means that maybe you don't have to, you have more stochasticity not being averaged out. So small bed size, maybe intuitively, it makes sense that you will have heavier tails with a smaller bed size. So increasing the step size, so based on the experiments we had, if you have a positive correlation between heavy tails and generalization, then this result basically would imply that small batch size is better for generalization. And I think many experimental papers have seen this kind of results. Although I should say in machine learning, you know, whatever statement you have in some particular network and some particular sort of problem, you may see sometimes a little bit of different results. It's not like it's not like pure math where you have a single result, but I think this would explain why small batch sizes can be beneficial. And also people have been talking about things like edge of cows and this kind of things that suggest that large step sizes, almost like as if you were going to explode, can help you out. So there are so basically some literature suggests that using large step sizes can be beneficial. And our result would also support that kind of empirical observation. And then we can study things like, as you can see, we have the relationship with the Hessian. So basically, depending on the Hessian, the curvature of your objective, we can also tell what kind of a heavy tails SGD will invoke at stationarity. So that's like kind of, if you go back to the previous picture I showed you, sort of you have a formula that ties all these things together. So all the question marks are like kind of determined by a single formula. Okay, I mean, this was, and then finally, for example, we can also find a critical step size where there will be a phase transition. This critical step size will depend on the batch size B, the dimension D, and the variance of your data, sigma square. So what happens is that if you have a tiny step size, less than this threshold, you will, at stationarity, you will have a power law decay, but you will still have a finite variance. That's the standard setting studied by giants like Nemirovsky, Polyak, and etc., where you can use CLT. But interestingly, when you cross this threshold, now you are pushing too hard and you blow up your second moment. So nothing is applicable anymore. And what will end up happening is that still some kind of moment will be finite. So you will be in the regime of heavy tails with infinite variance. And then there will be some sort of maximum step size. It's like almost things will explode now. And then if you cross that barrier, then you won't have a stationary distribution and everything will explode. Okay, so but basically this is telling you that, okay, even if you are in the linear regression setting, if you have a light tail data, if you choose your step size, batch size, or Hessian in a careful fashion, you will always end up landing in the heavy tail regime, right? So even if everything is sort of, it's kind of suggesting or complementing the experiments, right? In the beginning, you may have Gaussian-like behavior, but in the long term, you could see this kind of heavy tail behavior even in linear regression, right? Again, for more general models, for example, as long as you have some sort of growth conditions, you can also show that some sort of heavy tails will arise. We have some work in that direction, but a lot of times you have only lower and upper bounds on the tail index. You cannot get a quite tight characterization, right? And then this is also, this is also consistent with some experiments. I think in the literature, people call this the catapult regime. So if you have some step size that's like you push it so hard that your algorithm is almost going to explode. And I think basically sort of this result is in line with that kind of results that tell you that maybe large learning rate or step sizes can be beneficial. All right. And then we had a lot of we could also study the growth of the moments. For example, how fast any moments can grow, right? So we look at the peak moment, and x infinity is like your stationary distribution, and we could get bounds on, what happens to your peak moment. So obviously, if your tail index is alpha, you will be blowing up your moments that are larger than alpha. But we could characterize, for the finite moments, we could characterize things like how big they are and how fast you converge to stationarity in the Wasserstein metric. So the only thing here is that we had to use a Wasserstein P metric not a Wasserstein 2 metric because, the second moment may not be finite. So, but otherwise, this H function, if you notice this function, this function is really key to understand how fast you converge to your stationary distribution. And then we have several results that tell you that this H function will tell you the geometric rate at which you converge to your stationarity. So you have some sort of exponential like ergodicity, you convert, in an exponential fashion. And obviously then we can look at the light tail regime, meaning that maybe the second moment is finite, how fast you converge to the stationarity, and so forth. And then in the paper, we also have characterizations of like how fast you blow up certain moments. But at the end, we can argue that you will get heavier and heavier over time because you are blowing up some of your moments. All right, and obviously, because we have the generalized CLT, as I mentioned, if you were to look at your iterates and then scale them in the right way, so if you're not Gaussian, you're not going to use the square root n type of scaling. If you scale them in the right way, basically your averages will follow like an alpha stable distribution. All right. So this is, you can think this as some sort of result that's a little bit like Polyak-Judiski style result that tells you that, okay, if you average your results, you don't have to get a Gaussian distribution. You may get something a bit more general. This result, okay. All right. So then this is also beneficial because when you try to measure tails, it's not something easy to compute. But if you know that your limit is an alpha stable distribution, if you average the iterates, they're really better estimators for the tail index of alpha stable distributions. So, this result can also be beneficial in practice to you because it makes things easier to measure. So in the paper, we have a lot of experiments where we just first verify the results on a linear regression model. We have things like if you synthetically generate data, the tail index alpha will be monotonic in the bed size. The smaller bed size you have, as you can see, the blue plot is like the sort of the smaller bed size where you have a lower tail index, aka you have a heavier tail. So we kind of experimented with the parameters, and one thing that comes up a lot in the literature is the step size to bed size ratio. And our results tell you that actually if this gets larger, either the step size gets larger or the bed size gets smaller, essentially you will be having like a heavier tail like behavior. So your tail index will drop. Okay, and then we kind of experimented this also with different neural networks. So in the paper, we have tried VGG networks that has more than 1 million parameters. But here, for the simplicity of the presentation, I mean, this is a smaller network on the CFAR10 data set where we look at the tails and you have different layers. And just consistent with the theory, actually, our theory doesn't cover deep learning. We only cover linear regression theoretically. But in practice, you still see the same behavior. This step size to bed size ratio is monotonic in the tails. Right? So if you increase it, your tail index will go down. And this is the same behavior at every layer that you have in the network. Okay, this is nice. So then this question begs another question. So let's say that, let's say typically this is what you see in a deep learning scenario. You start with, let's say, light tails, alpha equal to 2. And then you get to this, your tail index drops, meaning that you are getting this into this heavy tail regime, right? In the well-trained setting at stationarity, let's say. Well, if the heavy tail is such a good thing, why shouldn't we invoke it artificially in the beginning, right? That's a question we may ask. Why are we letting SGD to kind of work so hard to get it? Well, if this is obviously related to the initial phase, how you initialize things. So traditionally, when people initialize the parameters of a neural network, aka weights of the neural network, they just go with a random Gaussian initialization with a particular variance sigma square. And this sigma square, there are different activation functions, meaning how you threshold the outputs of your neural networks. So basically, after averaging, you do some sort of thresholding, some sort of nonlinear thresholding that's called an activation function. So there are different variants of how you threshold things, but let's say for the ReLU activation, that's very common. You need to choose your variance in a careful way so that your network preserves the variance. Imagine you have a deep network with many layers. You don't want to blow up your variance, or you don't want to sort of decay your variance very fast. So the way it's set up is to preserve energy, if you wish. You keep the variance to be you keep the variance such that it's actually constant. But obviously, this is essentially avoiding you to have sort of very heavy tails, because all the variance is becoming sort of controlled, right? So then the question was, how should we choose the sigma square to preserve any moment? Let's say not only the second moment, but let's say if you want to be in the alpha less than 2 setting, for example, you may want to preserve the moment alpha. For example, you may just want to preserve the first moment, not the second moment, right? Obviously, intuitively, you can think that you should push a bit harder. You need to maybe sort of make your variance, let's say, not 2 over D, but something a bit larger, so that you will be a bit more aggressive to invoke the heavy tails. So in the paper, what happens is that if Gaussians have a lot of spherical symmetry, and you can do a lot of nice computations. So in the paper, we have more exact computations, but asymptotically, it turns out that 2 over D is the usual sort of variance that people set up. It turns out that you need to be a little bit more aggressive. And if you want to, let's say, preserve any given moment S, let's say S is equal to 1, you are preserving the first moment, then you want to be a bit more aggressive and have a corrective, you want to have this corrective term to be able to push it. So it's a bit like, because things are unstable, you can just think that you're dropping a pinch of, just pushing it a little bit lightly. As you see, it's a second order correction. If you push it too much, everything will blow up. So, but this kind of initialization, there are different activation functions, as I mentioned, ReLU, leaker ReLU, etc. For different functions, we have different formulas. But roughly speaking, it's something that's allowing us to invoke heavy tails right in the beginning. Let's say we can, if I want to get tail alpha, I can just set up S equal to alpha and I get it right in the beginning, right? So, and then actually in the paper, we show that if you have many layers, so, if the number of layers is going to infinity, actually we can argue that the forward step where you propagate input towards the output, as number of layers grow, we can probably show that you will have heavy tails. All right. In terms of essentially the forward propagation invokes heavy tails if you choose, even just at the beginning, if you choose things in a careful fashion. And in the paper, we have also some bigger experiments, but here, when we tried it with different well-known initializations, in the beginning, it wasn't an incredible improvement, but as you can see, we had some improvement. For example, the red one here, in the iterations, you see that compared to other iterations, our test loss is looking better, our train and test accuracy is looking better. I guess it's because we are exploring better in the state space. So this is a joint work with my student, Yuan Hu, graduated last year. So basically, you know, there's a lot of potential of invoking heavy tails in the right ways, maybe to be able to do better training. But we have to explore things a bit more, I will say. Another thing that we are interested in would be, so this theory and everything I was talking about is mostly for constant-like step sizes. But in practice, actually, people use things like cyclic step sizes, where you start with something small and then you go up and down in a cyclic fashion. And people also proposed random step sizes. Let's say your step size is in an interval, you just randomize it uniformly, let's say on the grid. And a lot of times, these step sizes can help you for some problems. And you could think of some heuristics why that should be the case. But there was no theory about it. And we weren't able to directly tackle generalization versus step sizes. But we thought if we understand the tail index as a function of your step size, then that can be informative because tail indexes are correlated with generalization. So what we did was, okay, we want to have a general class that will generalize cyclic and random step sizes. And of course, a natural candidate is to look at something like a Markov chain on a grid of step sizes, right? So a Markov chain in a special case we can reduce to an IID sort of step size. But also, you could, for example, if you have a transition probability P between the step sizes, you know, if you just choose it P to be 1, meaning that you are choosing things in a deterministic fashion, you could also recover cyclic step sizes. And then for this class, we can characterize a tail index, and that allows us to compare different step size schedules in terms of the tail index. And we could also still show things like monotonicity with respect to bed size, dimension, step size, etc. For this larger class. So this paper was published last year in TMLR. So here is just a sort of like illustration. Let's say you have a grid of step sizes, a small step size and a large step size. It can be a very fine grid, but let's just for simplicity, let's look at the case where you have only 2 possible step sizes. So, and then you have a Markov chain. Let's say for simplicity, let's take, you have a probability P to go from one to the other one, right? So if you choose P to be 1, essentially you are going back and forth and you will be in the cyclic step size regime. But if you choose P to be differently, you know, you will have a more general step size, right? P does not have to be 1. So we compare cyclic step sizes, IID random step sizes, meaning that let's say you just sample randomly on the grid, and the constant step size. Okay. And of course, for fairness reasons, the constant step size has to be set to the average of the random step size, you know, so that we are not comparing apples and bananas, right? And in the paper, we have all kinds of comparisons between different step sizes. But what's interesting is that these cyclic step sizes actually, we can prove that it will, you know, in settings, in some settings like the one in the figure, we can show that cyclic step sizes will invoke heavier tails compared to a constant step size. Same thing, the Markovian step size can even invoke heavier tails compared to a constant step size, right? So that's a good thing. So that tells you that Markovian step sizes that we are developing, where you transition between transition on a grid with a certain probability P, can be an alternative to traditional step sizes, right? Because if the if heavy tails is a good thing, then this sort of step sizes will actually have heavier tails. So that's one thing we had. Another thing we found is that if you have a coarser grid versus a non-coarse grid, the coarser grid will have a heavier tail behavior. And if your range is wider, we were also getting a heavier sort of tail. We kind of we kind of like verified this with experiments in linear regression, but in the deep learning setting also, when we look at the Markovian step sizes, of course, the theory doesn't cover deep learning. We can only do the theory for simple models. But even in practice, we have seen that for some problems, these Markovian step sizes was leading to heavier tails as expected and to better generalization as well. So this is basically, I will say, this allows us to, I think for cyclic step sizes and this kind of general step sizes, we are not aware of any other theoretical analysis that can sort of relate things in terms of, I think this is the only work that can explain the tails for these general step sizes that are used in practice. All right, and maybe I have 5 minutes, but maybe let me quickly tell you something quickly about, in 2 minutes, about the decentralized setting. So in the decentralized setting, actually, you have a network of data. For example, imagine your data is coming from your wearables, smartwatches, and sensors, cameras, and these kind of things. The data will not be sitting on a computer. It will be decentralized over some sort of computing agents, right? You may have a high connectivity like a complete graph, or you may have low connectivity like a circular graph. And what the decentralized, there are decentralized versions of stochastic gradient. Essentially what they do is because you don't have access to all the data, you kind of take local stochastic gradient steps. Every variable, you have local variables. You don't have the iterate xk anymore. But you also have a subscript that tells you, okay, this is the local iterate at a particular node I. Okay, but the main idea is that every agent sort of does some sort of averaging with the neighbors and then does some sort of a local stochastic gradient step. And you have a communication matrix that tells you how you are communicating. And there are different ways of choosing the communication, but I will say if delta is equal to 0, you are not communicating, no communication. If delta is positive, it means that you are communicating. And I will show you just one quick result. The question is, if you are on a network, what happens to your tails? For example, think about averaging can maybe taper down your tails a bit, right? Because you are averaging on a network. But at the same time, if there are some crazy guys on the network, right, that are kind of going a bit fast, they will also pull down other guys on the network. So it's not clear what will happen to your tails if you're on a network. And luckily, we can have a really nice formula that's like sort of that tells you that your tail index alpha hat, we know how it will change. We can do some asymptotics in the communication parameter delta that tells you how they will change. And the paper has a lot of details, but roughly speaking, interestingly, there are two regimes. If you have a very big enough network, it turns out that adding a network makes your tails even heavier. Again, if your step size is sufficiently large, adding a network makes your tails heavier. But it turns out that if your network isn't that large, or if your step size isn't that aggressive, when you add the network structure, your tail index will drop down. So your tail index will increase. It means that you will have lighter tails. So basically, it's like you have different phases depending on the parameters. This picture shows you in the large step size, large network regime, you can invoke heavier tails. But it's not always the case. So, to summarize, if I wanted to summarize, I think the stochastic gradient descent methods are really interesting methods. And we wanted to understand the heavy tails in that context. And I think there's a lot of work to do in this direction. What we did so far was that we kind of studied the tail index theory. And then linked it into different parameters. And because tail indices are related to generalization, one of my colleagues, Lin Zhu, will tell you more about tail indices and generalization tomorrow. So because they are linked to generalization, I think it makes perfect sense to understand them better. And here, we look into decentralized settings, different step sizes, and different step size schedulings. And turns out that by invoking heavy tails, you could also improve performance in some settings. Thank you so much for listening.
Okay, thank you very much, Mert. Do we have any questions?
So could you explain how you can apply the generalized CLT to the iterates when you don't have independence between the iterates of stochastic gradient descent?
Yes. So that's a good question. So essentially, even if you don't have an IIT, so for example, there are things like martingale CLT type results. So even if so there's a generalization of CLT to martingale CLT, where even if your sort of variables are not IID, you can apply it. So I think the standard reference would be the Polyak-Juditsky paper in '92 that does this in a really nice, analysis in a really nice fashion. So you can think that when you sort of come close to stationarity, even if things are not IID, you will still have some sort of nice maybe martingale decomposition, if you wish. But what we do is we also what we do is you can think that it's like a heavier tailed version of this result, where we build heavily on the existing tools. And Mirek also has a really nice result about basically non-IID sort of variables being average to be heavy tail. So in short, I mean, it's not an obvious result, but we didn't fully come up with it ourselves, to be honest. So we also use a lot of things from the literature. I'm happy to send you the references. Yeah. Thanks for the question. Yeah.
Yeah, thanks. Anything else? Okay, well, thank you very much.
Thank you so much for the invitation.